Welcome back to our discussion on the applications of derivative to economics, commerce and management. So, let us just recall in the previous lecture we looked at the notion of differentiability for special functions like exponential function, the log function and so on. And then we looked at its applications of the derivative, approximation of how derivative is used to find approximate values of a function at a nearby point. And that gave us some nice applications in economics and commerce, our subject. Namely, we found a relation, namely the marginal of propensity to consume plus the marginal propensity to save is a constant that is equal to 1. So, we will look at more applications of derivative in this today's lecture. So, let us just start recalling the notion of elasticity. So, recall that the price elasticity of demand we denoted it by the epsilon d. This is the epsilon, the Greek letter with a lower suffix d, indicating this is the coefficient of elasticity of demand. If the price demand function is p equal to f of q, then we define this as the percentage change in q divided by the percentage change in p. So, percentage change is in demand divided by the percentage change in p, and once you write the percentage in terms of the fractions, this just gives you that delta q by delta p multiplied by p by q. So, what is delta q? That is the change in the demand, right, q, resulting in a demand for p, that is delta p, at the price q, and at that point the price is p. So, that was how we defined the and we gave a reason why it should be defined this way. The coefficient of elasticity, this constant which gives the sensitiveness of how the function changes. So, we had a discussion in our previous lecture. So, we take it from there, and this is the definition of coefficient of elasticity of demand, which comes out to be delta q by delta p, change in q divided by change in p multiplied by p by q. For a linear function, if you recall, we saw that this was always a constant. Okay. So, we do not have to bother much, that was equal to the slope. For a general price function p equal to f of q, so it is natural to define, instead of delta p by delta q, it is natural to define replace delta q by delta p by dq by dp. We are not saying we are just replacing that fraction by this fraction. We are replacing the fraction delta q by delta p by the derivative of q at the point derivative of p with respect to q 1 over of that. Okay. So, here essentially we are assuming that dp by dq is not equal to 0, otherwise this will not, this formula will not make sense, right. So, the coefficient of elasticity of demand is defined as 1 over the derivative of p with respect to q multiplied by p by q. So, this is the definition of coefficient of elasticity for non-constant functions. For constant functions, this will come out to be same as the earlier one in any case, right. So, let us look at an example. So, given a demand function p equal to say 60 minus q square. So, here as you see that as q increases, the price is decreasing, right. As q is increasing, minus q square, that quantity will increase, right, and minus q square will become a larger negative quantity as q increases. So, p will become smaller. So, for this if we differentiate with respect to q on both sides, we can differentiate with respect to p on both sides if you like. So, dp by dp, that is equal to 1 is equal to 60, derivative of 60 is 0 minus 2 dq by dp. So, that means dq by dp is equal to minus 1 over 2q. This is the kind of thing we will do it very often. We will assume that dp by dq is 1 over dq by dp and so on, right. So, the coefficient of elasticity for demand at a price P, which we said is equal to dq by dp. So, this is dq by dp into p by q. So, that comes out to be p by minus 2q square. And if we put the value of in terms of p itself, okay, then this q square from here minus q square is equal to p minus 60. So, if we put that value here, so this comes out to be equal to p divided by 2 times p minus 60, right. And at a point say p equal to 44, okay, this is equal to, so this is elasticity of demand at a price p, right. So, if you want at a particular price, you put that value. So, in this formula we will put that value. So, we get this value. So, it is minus 1-1.374. So, the coefficient of elasticity of demand at a price 44 is minus 1.375. So, this is how we calculate. And if you recall, we had given interpretation of the elasticity for demand is when it is less than between 0 and minus 1 and minus 1 to infinity. At minus 1 it is unit elasticity of demand, and on the side minus 1 to minus infinity, this is the proportionate, this is the sensitiveness of the. So, this is how you calculate the coefficient of elasticity of demand at a particular price, and then you interpret it. Let us look at another example. We want to know elasticity of demand for a exponential function. So, let us say the price and demand are related by the function q is equal to a raised to power a into p raised to power b. Price is always a positive quantity, so that does not affect us. Okay. So, where a and b are constants. For this price and demand and price and demand function, what is dq by dp? If you take dq by dp, this is an exponential function with the base p, right. So, sorry, this is the power function, p is fixed, p is varying and b is fixed. So, the power is fixed. So, it will come b power comes down, p b power minus 1. So, dq by dp. So, for this is a power function. So, a b into p raised to power minus b, p raised to power b minus 1, differentiating this equation with respect to p. Now, we can put the value of on, right. So, the coefficient of elasticity at the price p is dq by dp, the derivative into p by q. So, this value is a b p raised to power b minus 1 into p by q. So, p and p, that gives you p raised to power b by q, and q is also equal to a b raised to power p. So, that is equal to b. So, coefficient of elasticity of demand at any price p is same value, that is equal to b, that is a constant for the power function. So, when the demand and supply are related by a power function, namely q is equal to a p raised to power b, then the coefficient of elasticity of demand at any price is the same constant as b. So, now it will depend upon whether this coefficient b is positive, negative and so on. So, let us look at we will look at this later on, what the implications this has. So, if b is equal to 1, right, coefficient of elasticity at every price is a constant, okay. So, and so on. So, that is how you calculate the elasticity of demand for functions which are not necessarily. Let us do a bit more of develop more calculus techniques to be applied to our subject. So, let us define what is called a we have already defined it actually. A function f is said to be an increasing function if this graph is rising up as you move from left to right geometrically. So, mathematically that means if x 1 is less than or equal to x 2, then f of x 1 is less than or equal to f of x 2. So, that is increasing function. So, let us assume our function is an increasing function, then what is the ratio of the change for any point c, f of c plus h minus f of c divided by h. Because the function is increasing, if h is positive, then c plus h will be on the right side of c. So, f of c plus h will be bigger than f of c, and h is positive. So, this ratio will be always a positive quantity, right. And if h is negative, then what can you say? F of c minus h will be a point on the left side of f of c. So, this quantity will be a negative quantity, and h is negative, again this will be a positive quantity. So, we can say we do not have to put this condition that h is equal to 0. This quantity is always bigger than or equal to 0 for all h sufficiently small, whether h is positive or negative. For positive it is obvious, for negative also it is h negative also it is obvious, because c minus h will be on the left side of c. So, f of c will be bigger than f of c plus h. So, numerator will be negative, h is negative. So, this ratio will be positive. So, this ratio is positive, positive we should say non-negative, because the function could be a constant. So, it is non-negative for all h bigger than 0 or less than 0 sufficiently small. So, that means in a neighborhood of the point c, this ratio is always a positive quantity. So, if the derivative, if the limit of this as h goes to 0 exists, because this is always a non-negative quantity, so the derivative also will be a non-negative quantity. The limit has to be non-negative. So, that is a property of the limit. The limit of a function, if a function is non-negative, then this limit cannot become negative. Right? It has to come closer and closer to a value, and that value cannot be a negative quantity. So, by the property of limits, limit of this quantity is bigger than or equal to 0, provided that limit exists, and if we assume that f dash the function is differentiable, then f dash of c is bigger than or equal to 0. So, what we are saying? What we are saying is, if a function is increasing and differentiable at the point c, then the derivative is bigger than or equal to 0. So, that is a conclusion that we are getting from here. So, we get if f of a b is such that f is increasing and differentiable, say at a point x, then f dash of x is bigger than or equal to 0. Right? So, that is the conclusion that we are getting. So, it is a property of the function over the whole interval a b. Right? If f is increasing in the interval a b, open interval a b, and the derivative at any point is bigger than or equal to 0, then increasing, then the derivative is bigger than or equal to 0. So, f increasing over the whole interval a b implies the derivative is bigger than or equal to 0 at every point in a b. A similar result will hold if f is decreasing. So, if it is decreasing, the ratio f of x naught plus h f of c plus h minus f of c divided by h will always be a non-positive quantity, will be less than or equal to 0. So, the limit has to be less than or equal to 0. So, a similar result holds when it says that if f is decreasing, f is we put both the words, this is wrong. So, we should not write this. So, f is decreasing and differentiable. So, delete this word, ignore this word. If f is decreasing and differentiable, then it implies the derivative is less than or equal to 0. So, there is a typo here. So, it is decreasing here. Right. So, we have got two important things, namely if a function is increasing in an open interval, then derivative is bigger than or equal to 0. And if the function is decreasing in an open interval and differentiable, then the derivative is less than or equal to 0. So, both the conditions have to be satisfied, increasing and differentiable, right, implies derivative is bigger than or equal to 0, and similarly decreasing and differentiable implies the derivative is less than or equal to 0. We would like to prove a converse of this theorem, and for that we need a result called Lagrange's mean value theorem, which in itself is one of the important theorems of calculus. So, let us state that theorem, what is called Lagrange's mean value theorem. It says that let f from a closed bounded interval a b to r be a continuous function. So, first of all, the function is defined on a closed bounded interval a b such that, so here should be a gap such that f dash exists on a b. That means, the function is differentiable on the open interval a b, at least that much should be there, and it is continuous on the closed bounded interval a b. We did not prove this property that differentiability at a point implies continuity. That in fact, when we did approximations, one could have easily shown that property. Probably let me fill that gap by showing you this now. So, let me show you that result. So, supposing f from a b to r and c is a point belonging to a b. F differentiable at x is equal to c. So, what does this imply? This implies that f dash of c, which was the limit h going to 0, f of c plus h minus f of c divided by h, this limit exists. So, from here what we got was f of c plus h minus f of c was approximately equal to h times f dash of c. What is the difference? We can write that is equal to plus h times some quantity, let us write the error that we are making, right, where this error goes to 0 as h goes to 0. That is what we saw in the approximations. So, if this, let us recall this equation. So, this is true. So, what is the limit of this as h goes to 0 at the point f of c plus h minus f of c. So, that will be equal to, by limit theorems, it is limit h going to 0 of f dash h times f dash of c plus limit h going to 0 of h times a quantity epsilon h. But observe is h times a scalar. So, this term goes to 0. So, this term goes to 0 and this is also going to 0. So, this limit is equal to 0. So, limit of f of c plus h minus f of c is equal to 0. We can write this as limit h going to 0 of f of c plus h is equal to f of c. So, this result can be written as this, and that means what? That says that f of c plus h goes to f of c as h goes to 0. So, that says, so differentiable, so implies f continuous x is equal to 0. So, what we are saying is, if f is a function which is differentiable at a point c, then it is also continuous at the point x is equal to c. Of course, note that the converse does not happen, that f, we said f differentiable implies f continuous. The converse need not hold. That means, f continuous at x is equal to c need not imply f differentiable at x is equal to c. For example, if that was the case, then what was the need to define differentiability? That is an obvious thing to say, but we can have an example if you like. Look at the example f of x is equal to x, say mod x for every x belonging to R. So, for this function, if I look at the graph of this function, the graph of this function looks like, so this is y equal to x and this is y equal to minus x. So, that is the graph of the function y equal to. So, it is continuous, but at this point you cannot draw the tangent, it is not differentiable. So, you can prove that rigorously also. So, let us come back to our statement of the theorem, that is Lagrange's mean value theorem. It says if a function is defined in a closed bounded interval and it is continuous on the closed bounded interval, in the whole of the interval it is continuous including the end points, and differentiable in the interval a b. So, differentiability in the open interval a b will imply differentiability in the open interval a b, but this need not imply will imply continuity in the open interval a b, but it need not imply continuity at the end points. So, we need continuity at the end points a b. Then the theorem says if these two conditions are satisfied for the function, it is continuous in the closed bounded interval and differentiable in the open interval a b, then there is at least one point c belonging to the open interval a b, say that the difference f b minus f of a is equal to b minus a f dash of c. This does not look like a very great result written this way, but supposing let us rewrite this as a is not equal to b, let us say, and divide by this, that gives you f b minus f of a divided by b minus a is equal to f dash of c. Then what does this ratio f b minus f of a divided by b minus a signify? That is the slope of the chord joining the point a comma f of a with b comma f of b on the graph of the function. And it says that the slope of the chord joining the endpoints of the graph will be equal to the slope of the tangent at some point in between. And that looks like a very profound geometric statement. So, let us look at that statement. Let me show you that in a dynamic geometry environment. What do I mean by this statement? So, what we are saying is looks too big. So, let me shorten it a bit and let me zoom out a bit more. Okay. So, now that is good enough. So, this green one is the graph of the function on the interval a b. So, this is the point a somewhere here and this is the point b somewhere here. If you want, I can locate this point a and b both. So, let us locate the points by drawing lines perpendicular. So, let me draw a line here and draw a line here and draw a line here and a line here, and let me find out these points of intersection of these two. So, intersect. So, let me intersect this and this and this. Okay, it has not taken that. So, let us select intersect. So, intersect this with anyway, let us not bother. So, this is the point A and this is the point B. So, in this interval the function is defined and this is the point A comma f of A and this is the point A comma f of B. So, looks like a nice smooth curve. So, let me draw the tangent to this curve at some point. So, let us So, let us view algebra and that point A is not visible. So, let me make this point A visible. Okay. So, let us show the tangent at a point. Okay. So, this is a tangent at a point A and let us move this point A. Okay. So, let us move this point A. So, you see if I move this point A, this number is showing me the slope of this tangent line. What is the slope of this line? See, I have computed the slope here. Slope is when the difference is 1 in the x coordinate y2 minus y1 divided by x2 minus x1 for a line. So, if x2 minus x1 is 1, so the height gives you the slope. So, that is the slope of this line. Okay. So, slope of this line is 1. So, I would like to find out this is the tangent, its slope at this point is 2. I would like to see whether there is a point where its slope becomes equal to 1 or not. So, you see if I move the point up, so slope is increasing because it is sloping more and more. If I go down, the slope is decreasing 2.6, 2.5 and 2.4, 1.7, so 1.4, 1. So here, so now so that means I have got the tangent parallel to the chord. So what it says is, for the theorem says that if the function is continuous in the closed bounded interval a b and is differentiable, that means at every point I can draw the tangent, then there is a point on the graph where the tangent is parallel to the slope of the chord. So that is I shown you dynamically that yes, that actually happens. Okay. So so let us come back to our theorem, namely, so this is what the theorem says. It says that for a function defined in a closed bounded interval a b, if I draw this chord joining the endpoints, the function is continuous in the closed bounded interval, differentiable in the open interval, then for some point c on the graph, the slope will be equal to slope of the chord. So this is a very important theorem in calculus. You will see many of the outcomes of this theorem, and we will discuss it in our next lecture. So in today's lecture, what we have done is, we have looked at the notion of coefficient of elasticity of demand for a general function, and how derivative is used to define the coefficient of elasticity of demand at a price p. We looked at some examples. Then we looked at how calculus can help us to relate it with the property of the derivative. So we said if a function is monotonically increasing, then the derivative, if a function is monotonically increasing in an open interval, then its derivative must be bigger than or equal to 0. And if a function is monotonically decreasing in an open interval, then its derivative should be less than or equal to 0. So we looked at those two properties, and if we will see some more consequences of that as a consequence of the Lagrange's mean value theorem, which we proved last. So we will continue this in the next lecture. Thank you.